On that note, let's go ahead and get started. Welcome back. I'm glad we're on a happy mood. Maybe you took a couple days off of this class, and I think that's great if you did. I want to kind of jump around a little bit today in terms of topics. So, as always, we have this material we're kind of trying to cover together and learn about in class, and then you have the lab, which is obviously at various points in the semester taking a larger amount of your time. And I do try to keep things a little bit synchronized so that the lab work feels meaningful and relevant, and as well as the in-class time that we have together. So there's a lot of things I want to talk about with regards to various buffers that are in use, and we'll talk about Z-buffer method today. Then I'm going to kind of skip a topic, and we're going to talk about shaders so that as you work on MP3, while we have kind of a very high level talk about them, let's talk about them properly so that you don't feel that you have to kind of learn it all yourself as you're working on MP3. So a little bit of a jump, but then we'll come back to the fifth learning module, which is that viewing and transformations, which is also important for MP3. Just looking at it where we are, I think it makes sense to kind of reverse the order of them right now. Where we left off, though, a week ago, before our demo day on Tuesday, is we were looking at different approaches to kind of deal with sort of the 3D issue. Basically, how do we determine what objects in a scene should be displayed or not? This was related to this topic of clipping and culling, where for the most part we were looking at 2D examples, which was, if you remember, we have a triangle, but it's not actually going to fit within our valid viewing range. How do we determine what that new shape should look like? That was all in 2 dimensions. There's a similar kind of issue, not directly related, but similar in concept with regards to that 3rd dimension, which is how do we determine if for a series of objects that we would like to draw that are potentially overlapping each other in that 3rd dimension, which one should be drawn in part or in whole, which one should be removed entirely. We kind of hand wave the so-called painter's method. The high-level version of the painter's method is that you're a painter, so you start in the very back and you draw the background, and then you draw the next level, then the next level, and the next level. That's why it's called that. It's essentially attempting to sort either at application level or in hardware your primitives so that you're drawing them from back to front. That is not a commonly used approach. There's a potential to believe that doing some object sorting can still lead to better performance in terms of these complementary methods, but this method is a much more common and popular one, the so-called depth buffer or Z-buffer method. What we do here is we essentially, as we are rasterizing our primitives, we're keeping track of, and we're also rasterizing or interpolating that 3rd dimension, that depth information that's associated with our primitives. We are going to be storing those values in a completely separate buffer. That's the Z buffer, or that we call it the depth buffer. It's the same term, they're synonymous terms here. We store that information in that additional buffer. When it comes time in our render output stage to actually take our X, Y, and color information and determine that, yes, we're going to be writing to our color buffer, we first do effectively an if statement. We are going to draw this fragment to our frame buffer if it is closer to where we are looking than what the previous thing that was drawn in that same location is. That's the depth buffer method, the Z buffer method. Talk a little bit about what that means in practice. Ultimately, it's an additional buffer, and it's an if statement associated with that buffer. That's really all that's going on with this method, but it is kind of a ubiquitous method for dealing with depth information for rasterization-based rendering systems. We have not talked in much detail about viewing and transformations and the viewing plane, but this is one way to at least start with by visualizing 3-dimensional geometry in a scene and what that may lead to in terms of 3 different primitives here. You can just think of them as triangles if you don't want to worry about more complex primitives. 3 different primitives rendered at 3 different times. Ultimately, for a given XY location in our viewport space and our screen, we are going to have just one, unless we do something else, one of these values be actually displayed, stored in our frame buffer, actually displayed on our screen. The question then becomes, how do we determine which of these 3 fragments are the ones that actually get displayed on our screen? They may have very similar XY locations for these primitives. Internally, there's an XY that's identical for all 3. What we then have that allows us to determine this would be that 3rd dimension, that depth information. And for now, we can just think of that X, Y is again, X and Y in our Cartesian plane. Our Z is effectively how far are we away. How far are we away from what we are looking at when we're trying to display a screen, a scene on our screen? We haven't been dealing with Z a lot yet, so we've kept it at 0, and you can still keep it at 0 this week and next week in the lab, and it doesn't really impact anything. And similarly, you may still get good results if you keep everything at 0, depending on what you want to show. The only example for which I think that has any relevancy so far would be that random triangles program. That was just drawing random x and random y with no z value, and you got effectively a painter sort, a depth sorting approach where we just draw the first one, then we draw the next one on top of it, and what you see are partially occluded triangles on top of each other. If we wanted to make sure that only those triangles that are supposed to be closer to us are the ones we would see, this is where this depth buffer method would become relevant here. In terms of generating these z values, it's the same thing as any other rasterization equation. So this slide is correct, but not super relevant. We have our plane setup, our line setup leading to our plane setup. We have our attributes that we know at the vertices of our triangle. And then for the same reason we can do so for color, for any other attribute, we can also do for z. We initially calculate as we go in the plus or minus 1 delta x direction. As we go in the usually positive delta y direction, we calculate with our triangle setup or our primitive setup, how much should these other attributes change when we go plus or minus 1 in those x or y directions here. So the equation is still the same for a plane ax plus by plus c z plus d equals 0. Otherwise, if you want to just not worry about the plane equation and say, we can set it up knowing what the change is in x, knowing what the change is in y, and calculate what our step change needs to be, then the same exact rasterization hardware that we've already talked about, that you've already built, that seems to be working, although which group was it that went back to test their old code and found that it wasn't working anymore? It happens all the time. And I don't have a good explanation for it, that you come back to the code 2 days later and it stopped working. What'll really annoy you, come back to it 2 months later and nothing works at all. That's just how it goes. So I'm sure you'll fix it again and you'll get back to where you were. But the same hardware you had, current bug notwithstanding, should just work for this. As long as, and you may have to double check that in your actual triangle traversal, triangle setup, and triangle test to make sure you actually didn't skip z. Because again, for the MP2 examples, you wouldn't have noticed any difference if you had skipped a z or not. But otherwise, it's the same exact rasterization. Think of z as just any other attribute. Or conversely, think of any other attribute as just a third dimension, an independent third dimension of our x and y. So you can think of it as x, y, red, and then there's a gradient of red across x and y. Or think of it as x, y, z, and then there's a gradient in z across our x and y. Same exact triangle setup, the same exact traversal, same exact Bressenham's kind of interpolation step is exactly what can happen for our z as it happens for all of our other attributes like color that we are interested in here. So the basic line buffer, or excuse me, depth buffer algorithm then requires a separate buffer. So you can think of it as just a separate region in memory that usually I would think our driver needs to configure for our hardware to take advantage of. And it would have the same XY resolution as our color buffers would have. So for every possible XY location, 1920 by 1080, you would have the actual front buffer, what's currently being drawn. You'd have the back buffer, what's currently being updated to be drawn next time. Sometimes there's that third buffer for triple buffering. There's many other buffers, but at the least there'd be this one additional buffer for that depth buffer or that Z buffer information. That's the XY resolution. The actual precision of it is something that is left to us as an implementation detail. There's an expected kind of dynamic range, typically between 0 and 1, but in OpenGL, it's one of the many things you can configure where you can say, I want my depth range to be 0 to 10 million, and then that would change the values that are stored in your depth buffer. But I think without losing too much generality, we can assume 0 to 1 as our depth range, 1 then corresponding to objects that are as far away as possible but still potentially visible on the screen, 0 being as close as possible to what we'd want to see in our scene on the screen. So we would set up, and just like if we want to clear our screen at the beginning of every frame, GL clear buffer we would call, or GL clear we would call, with the GL color buffer that we want to actually clear. We would also then want to reset this frame buffer, this depth buffer as well. So you're basically doing both. You can do both in a single call, but in terms of like DMA operations happening in the system, to use depth and to use the Z buffer method, you're basically doing two clears of two buffers for every frame in our scene. So that's what's kind of being visualized as happening right here, is this sort of pseudocode approach. We clear our frame buffer, as we already are, with whatever our background color is going to be for that application, for that scene. We're also going to clear to whatever is initialized as Z far for that particular scene. For 1.0, we can just assume that for now. You can specify it, and then we got to make sure, just like we can change the background color, we can change the background depth as well and work according to it. So as we rasterize and as we're processing each polygon in our scene, we do everything we've already been doing, figure out what the other attributes are going to be at that XY location, also figure out what that Z value is going to be at every given location. Again, hopefully your hardware is already doing it, but what you're probably seeing right now is you have your triangle and you have Z of 0 for all three vertices in your triangle, and so it may be hopefully correctly rasterizing and interpolating, but it's interpolating between 0 and 0, so you're not seeing anything change in your simulations or anything. But eventually you'll have a triangle and it'll have some three-dimensional structure to it, and one vertice would be very close, one would be very far, and then you'd have to, based on the size of that triangle, interpolate those Z values across each line and down each raster line as well. So otherwise, in terms of rasterizer, nothing should really be changing from what we were already doing. Now, to accommodate this, we have to do the clearing of the background every frame for that particular scene, and then in our render output, where we're actually now calculating, given an X and a Y and an RGBA value, update this location in the frame buffer. There's now basically this if statement that we're adding as well. We take the X and the Y. We can probably still, in parallel, calculate a couple of addresses. And I think if we keep the bit depth the same in our hardware, like 4 bytes per pixel as well as 4 bytes per depth information, then you don't really have to do much more arithmetic in your render output. Because given an X and given a Y, you can calculate Y times stride length plus X, and then to get your relative address, then you add it to your base address. You just basically do that step twice. So you add it to your color buffer base address. You then also take that address based on X and Y and add it to your depth buffer address, and you would do a read before you do your write to your frame buffer then. You do a read to check, at my depth buffer at that same exact location, what is the current depth value? It will be, if you've set up the OpenGL part of your application correctly, it will be something. Because at the beginning of every frame, just like you have a background color potentially with GL clear, with that same GL clear call, you can also say initialize all Z values to be 1.0 or whatever value you initialize it to. So in your render output, a little bit of extra arithmetic to check, to calculate a new address, and an additional state that's basically read the depth buffer at this address, and then one more state that's going to do a comparison logic before you write anything to the frame buffer. Take the Z value that's an input to render output at this stage, determine is it less than what the current depth buffer is at that location. So literally if Z is less than return depth buffer location XY. If it is, actually output the fragment to that location in my frame buffer, and then also you have to then go back and update the frame buffer as well. So just like we have a clear background color to our scene, we also have kind of a far background depth to our scene, and now our render output's gotten a little bit more complicated because we are doing kind of a read, modify, write operation with depth, but only if we pass the so-called depth test at that stage. If we wrote a triangle that's very close to the screen, then we try to write a triangle or say a fragment in a triangle that's further away from that location in our scene that we have here. We'll go through all the steps for that second triangle. We'll do all the rasterization for that second triangle. When it comes time to actually write those fragments for those triangles, when we check the depth buffer at that location, X, Y, we should find, oh, we've already written something this frame that's actually closer to the screen than what was already written. And then consequently, this very high-level visualization here, unlike in the painter's method where it does matter quite a bit, which one do we render first, S1, S2, or S3, with the depth buffer method, it shouldn't matter at all in what order we render them. You could argue there's an efficiency issue in terms of which one we do first, but even if we do them in an exact backwards order, we're still going to be okay. For this S3 and this XY location in S3, we would compare against the maximum depth. Passes the depth test, we draw that fragment, we draw all the fragments. Next we move on to S2, we check the depth location at that XY location, and presumably all those overlapping XY locations. The depth information, assuming the way we've set up our scene that S2 is closer than S3, would be a smaller value. We then update our depth buffer and we overwrite the value there. Then finally we do so for S1. We should get a smaller Z value for S1. We should then be able to update it. So this allows us to send those in any order. If we did them in opposite order, kind of the converse operation would happen. S1 would happen first. It would be closer than the far depth buffer, the reset value. We would update it. When it comes time now to render S2, we would check the depth buffer and the Z value would be larger and say, oh, this is actually further away. That if statement in your state machine doesn't progress past, you just drop the fragment at that point. We don't do anything with that fragment, at least in this rendering mode, because it's further away. You could argue we wasted all the effort in rasterizing and all that, but you don't know necessarily. You can do some initial depth painter style sorting and determine, hey, S3 is entirely behind S1. Well, let's just drop it entirely. But even if you don't know that, yes, you are rasterizing all these primitives, and depending on the order in which you do so, you're dropping a lot of fragments along the way. But that's why when we get to MP4, this will be a pretty small part of MP4. I think you'll be able to figure it out. So there's one API call, GL clear, which you've already looked at. There's some additional testing to make sure your rasterizer does what you think it should have been doing back in MP2. And then there's like 2 or 3 more states in the render output to do this depth buffer approach. And to be honest, that's kind of all I really need to say about it. I can show an example of it in practice, but the truth is it doesn't really look like much. Because it's just objects in front of other objects. I mean, yes, so I'm showing you that depth actually works, but it's kind of hard to show very much that, yes, so we have this cone, and there's depth information, and you can, for this basic example, you can look at the wireframe if that helps kind of visualize what's happening here. But one object in the Z dimension is in front of another object, and for some of those fragments, independent of what order we rasterize and we set up these objects and rasterize these triangles, some of those fragments will pass the depth test, others will fail the depth test. And the end result is what I think one would hope when setting up a 3-dimensional scene. This is a very classic kind of OpenGL demo scene of sphere being in front of that cone, and we keep the fragments that we want and we drop the fragments that we don't need. So that is a demo of it working. It doesn't, it's fine, it's correct. It doesn't really look like much, I guess. So any questions about depth test? It'll be a couple weeks, and it'll be part of other things you're doing for MP4. But I think you could probably assign one team member to be the depth test person, and I do think you'll be able to get it working. I guess the only difference would be for render output, we've only been writing to memory to date, and this will be read followed by potentially 1 or 2 writes or 0 writes afterwards. But for MP3, you'll be doing reads already, so I think you'll get comfortable with reading from the cache that we have there. Otherwise, it should be quite similar to what you already have in render output with just a couple more states. So one more thing I want to talk about, and we'll get to this here with regards to render output. There will be more things beyond today. But first, this view of the buffers of the system, I think, is an important one to start to build. Maybe you've looked at the driver code and you can already have some appreciation for what's happening with the buffers, but I kind of like this visualization of ultimately what's happening. So for a given resolution, you have at the very least a front buffer. You have, here's what I'm drawing to my screen at my 1920 by 1080 resolution here. But you also have, in addition, all these other buffers that we'll start to see, some of which we've seen, some of which we will start to see, that allow us to do other operations that are also effectively at that same resolution. So when we talk about how much memory you need for your GPU, it's going to be a function of the maximum resolution for a particular scene that you'd like to be able to support, but it's not quite so simple as saying, well, we want to support 1080p, so 1920 by 1080 by 4, the kind of calculation we did before of how much throughput do we need, how much memory do we need. That's the kind of the starting basic amount of memory we need, but there's that depth associated with it. It's many, many such buffers potentially that we may need to then access many times per frame. Another way to think about that is, for a given scene now that we want to do at our 1080p resolution, we now can look at it and say, independent of all the shading that's happening, well, at the very least, we need throughput or bandwidth for clearing the color buffer, GL clear call. So we have to write the 1920 by 1080 locations to start with. Well, now I'm telling you, you also have to initialize the depth buffer as well. That's another write to 1920 by 1080 memory locations. Now, for every single fragment we want to draw, which is going to be more than 1920 by 1080, because it's going to be more than just a single quad or a single triangle we're going to want to draw here, but for every single primitive we want to draw, we are potentially doing what? We're potentially writing to a buffer, so potentially 1920 by 1080 writes. We're then doing a read and potential modify of our depth buffer, so that's another 1920 by 1080 reads or writes, reads and or writes associated with it. So as we start to look at modern devices and see, well, look at this incredible amount of off-chip memory bandwidth they support, there's still need for more and more. We're still not necessarily coming at all close to maxing out our memory needs here. But this visualization, I think, is a good one to have of what we have going on in our system. Front buffer, back buffer, maybe a third color buffer, although I don't think our driver is currently using it. At the very least, a depth buffer. Let's look at a couple of other examples of how we've used buffers historically in computer graphics. I like to go back to kind of early video game systems. They were simpler. This could be a separate course where we could just do 2D computer graphics. In early games, we had the so-called concept of sprites, and that was one method we could integrate kind of unrelated bitmaps and kind of paste them together so that they all appeared to be part of a single frame. In those early video game systems, both PC-based as well as dedicated hardware consoles for it, essentially the main hardware that the GPU term didn't exist, but some sort of image processing, pixel processing, graphics unit, they were basically one or multiple DMA engines. And as you look at the SGP design that you're working with, while you haven't had to change it yourself, you can see there's many DMA engines in that system for basically the same kind of reason. So in a lot of those early systems, what you would have would be a separate memory that would hold the individual sprites. And based on how much bandwidth you had, as well as the particular hardware capabilities, your draw calls, how I would actually draw a scene, would be a series of copy-paste operations from the sprite buffer, sprite memory is what they would call it back then, from that buffer to what we'd actually want to display on the screen based on some aspects of maybe changing the color index associated with it, translating it to a new XY location, sometimes scaling the buffers as well, and then maybe allowing for transparency of how we copy things back over. So while we don't do a lot of sprite programming anymore, what's not shown here would be all the texture buffers we'd have to set up. That's how we would do so today. The same concept kind of still applies directly to the kind of compositing operations we still actually do have to do today. Here's some random sprites. How many old school gamers do we have here in class? One. That's one. Then I won't do the quiz of who recognizes all the sprites here. One of those is not a sprite, just a random image from a Wikipedia page. But the rest are sprites, I believe. That's definitely Battletoads. Okay, no pressure.
It's okay. The middle top is Legend of Zelda.
That's Legend of Zelda. Tossing swords at you. It's Kirby. That's not a sprite, though. I don't know why I grabbed that one.
I don't know who the top right corner is.
Okay, I'll leave it as
that
a.
one's Alucard from one of the Castlevanias.
That's Simon. That's Simon. Yes. Okay. Close enough. Yes. Yes. Castlevania one.
I don't know who that
Okay.
I know Mike Tyson's Punch Out.
It's Von Kaiser from Mike Tyson's Punch Out, of course. Who's this guy?
That's from one of the Contra.
That's Contra. Okay. You're doing very well on this. I'm impressed. Oh, that's funny though. If this was a question I asked 20 years ago, this would every single person would know exactly every one of these because it'd be just burned into your retinas and you'd have no choice but to know these. Okay, very close. Who's this one?
That is from, it's that ninja game.
Ninja Gaiden, yes, okay, that's him. Ryu Hayabusa.
I don't know that guy.
Okay, we'll leave that as him. And this one, still a game that just came out very recently again, a most recent version.
Samus.
That's Samus from Metroid. Okay, very good.
I don't know the mohawked.
That's Bebop, of course, from Ninja Turtles. Okay, and that's the Red Mage from Final Fantasy. So, okay, just want to make sure.
I haven't played the original one.
It's been a while. Okay. All right. Thanks for humoring me briefly with that, and you get a reasonable pass. The class gets a reasonable passing grade on knowing our sprites. That's kind of why I got into computer graphics in the first place. First off, it is interesting from an architecture perspective. But back when I was younger and had more free time, I certainly, lost many hours to these kind of games. And now I have time maybe to try slaying the spire once a week or something like that, and usually failing. I do, yes. Good taste in many things. Okay, so this would be our generic sprite processing architecture, and it's not that different from a lot of what we have in our pixel pipeline now, which you're not using a lot of that directly because I kind of set up a lot of that driver stuff for you. It's all there, it's all working behind the scenes, but that's how we're basically clearing our color buffers, clearing our depth buffers as well. And I do think it's important that we understand that DMA concept. If you've taken some embedded systems classes, hopefully it's kind of covered there as well. But just to reiterate, even if you've had it or you don't remember it, DMA stands for direct memory access. The idea being, and if you want to think of that as a state machine, that's all it is at the end of the day. The idea being we have this separate piece of hardware whose job is basically to offload from the CPU block memory operations. We could always have a system that doesn't have a DMA. It's never strictly necessary from like a functional correctness perspective. But let's say I want to copy this Space Invader to this location on the screen. What that would require in software would be a series, a set of for loops, right? A two-dimensional for loop for X dimension, for Y dimension, do a read from this memory, and then do a write to that next memory. And that's what the CPU would effectively be doing. And it'd be stuck doing that because there's a lot of things we're always wanting to copy over. Read location, calculate read location, calculate write location, read pixel, or read sprite, or texel, write to location in memory, increment our pointers accordingly. You could write that for loop in C or whatever programming language of choice. The DMA engine is essentially a state machine that does that for us. What the CPU then does is it kicks off or it configures that transaction and it says, I want you, and this would be in the context of a game or any given block operation we want to do, I want you to copy from this location. I think I might have had some little visualization here. There we go. I want you to copy starting from that location at pixel location 0, 0 in the sprite buffer to 24 by 24. So give me the next 25 pixels or what have you at this starting location. And I want you to copy it to that location in this other memory. And whatever API is provided really depends on the underlying system. In early days, there was no API. It was very low-level kind of assembly style calls. Now we have block buffer commands. There used to be GL copy pixels was a way we would do these kind of operations. But that's what the DMA engine would receive those commands. It would say, here's my starting location, here's my for reading, here's my starting locations for writing. Here is kind of usually, in this case, a two-dimensional kind of structure that I'm copying. Here is potentially, depending on the system and the capabilities, other things I may want to do. In this case, it could be take the values and scale them by a factor of 1/4 to make it smaller on the screen than it might be in the sprite buffer. Usually the scaling would work in the opposite direction, but scale it in one way or the other, and then just go. And then this little line would then effectively be just a kind of I'm done result coming from the DMA engine to the CPU. Oftentimes in modern systems, that'd be via some interrupt mechanism where a flag would go high and say, I'm done, get back to doing the next DMA transaction. Otherwise, the CPU could just be occasionally polling that result and checking like a ready bit in the DMA. But this is a very common way, we do all sorts of memory transactions in all, computing systems and certainly in all embedded systems. The CPU could do that operation itself. It's capable of doing that operation. The DMA can be thought of as an accelerator. At least it's an offload engine. We give it a couple quick little commands, so we send it a few little codes in its configuration registers ultimately. We tell it to go. We either poll and monitor, or we get woken back up when it's actually done. There's no real guarantee it's necessarily going to be any faster than doing it through the CPU, but it might be a little bit faster, right? It's custom hardware that only has to do read and write operations. It should be able to be more efficient at doing things like incrementing the pointers. It's not having to process and decode instructions. It's just reading and writing to memory. We have a few of these in our current system. The concept is as old as computing from the 1980s, and so they're used for sprite buffers. We're still using it today. In OpenGL, conceptually we can think of memory as I had that view as a series of those two-dimensional arrays corresponding to our resolution. OpenGL has a separate way of working with those buffers than it does working with fragments. So old school dedicated functions were things like GL copy pixels. Now it's all going to be those buffer array objects in which we're initializing these additional buffers and we're telling it to do these copies of one particular buffer or another. We'll learn more about those buffer operations as we start to learn about things like texture mapping. The early 2D systems had a special piece of hardware for the term was called bit block transfer, and then the piece of hardware started to become kind of colloquially known as a blitter, and as a special hardware for merging source and destination pixels from these copy operations. Back in the early days, this was usually a 1-bit operation, so we'd have a 1-bit source buffer, an additional 1-bit destination buffer, and this operation would allow you to do kind of custom merging of our source and our destination. The term we use now is compositing or blending. It's conceptually extremely similar, but it's actually a little easier to think about it as a 1-bit version. So there would be a piece of hardware that would basically be situated here, that would take as input, and again, think of this as the whole buffer, or think of it just for a single XY location, it's exactly the same. A source pixel that I want to potentially write to my destination. Think of it as the frame buffer, that's fine. As well as the current value of the destination, and it's going to merge those two results in some way, shape, or form. We don't do this currently in our render output. We will, for MP4, we'll start to do this in our render output as well. Not just doing all the work of determining should we write this pixel or not, with the depth and other things we can determine to do that, but also should we merge the results we're writing with what's currently in the frame buffer at that particular location. Again, just a couple more states in our state machine, but there are more that we'd have to do here. That's what this so-called blitter hardware would do. If it was a 1-bit value that takes just 2 inputs, source pixel, current destination pixel, otherwise read that S and D is what we want to write now, what we had previously written at that location. If it takes just 2 bits as input, there's really going to be just 16 different potential functions it could be configured to do. It would just be a lookup table, a 4-bit lookup table we could potentially program. That would be all the blitter hardware would have to be. You could also do it with gates and with muxes, because not all of these operating modes necessarily make a lot of sense, from a graphics perspective. Given an S and a D, if they're 1-bit values, there's just those 4 permutations. Yes, we're going back to 281 today, just briefly. 4-bit values where our source is 0 and our destination is 0 or 1, so you get those 4 permutations there. That is the input, so that doesn't change. There's 4 entries in the truth table for that particular function. But then the truth table itself is going to then be a 4-entry thing, so there's technically 16 different possibilities of what could be in that 4-bit truth table. It's very similar to how FPGAs work now, right? Where you have a lookup table for the actual logic we want to instantiate in the FPGA. We're programming the individual bits of the lookup table. So you could think of this as a 2-LUT, a 2-input lookup table for our bit writing modes here. And we have various different functions we could support here. What would function number 3 do, this red vertical box that I have drawn here? Takes a source bit, takes a destination bit, sure. It passes through S, just to overwrite, thank you. I didn't know the answer when I asked the question. It's an overwrite mode, which we don't always have to do blending or compositing. We want to say we have a new pixel, we overwrite the old pixel at that location. How about function 6? XOR gate, right? So I think it's a truth table, right? So we know what these are. How about function 7? It is an OR, yes, okay. And should also be here. Which one would be and? Would be function 1 would be function and here. I think we can think of reasonable reasons to do function 3. Let's talk about why we may want to have function 6 and function 7 here. So you're right, this is a 281 style truth table with source and destination, but don't overthink it. Given the truth table, given the 1s and 0s, 3 is literally just passing through S. 6 is going to be an XOR, right? 6 only outputs 1 when S and D are different from each other. So it's your XOR, exclusive OR. 7 is an OR. As long as S or D is 1, then it passes through a value of 1. Only when they're both equal to 0 does it pass through a value of 0 here. But that's how we did initial kind of blending and compositing in systems before we had true kind of alpha blending in the day. So originally that's how we would do blending. There'd be effectively just a single bit of transparency or a single bit transparency mask. It's all we actually needed, and it still could be used today to kind of overlay images with transparent regions. Had to use the blitter hardware or some equivalent of the blitter hardware. Let's say we wanted this to be our background, and we wanted to overlay our background with this, whatever pellet, whatever object that corresponds to, right? So you would first you would AND it, the background, with the black on white mask of our transparency mask here to get I don't show the intermediate step, unfortunately. You would first AND it to show this basically with a hole inside it, and then you would just OR the result with the actual sprite value we'd be interested in. That allows you to do it without any kind of depth information. There's no depth information associated with this, at least in the rendering side of things. 2 passes, 2 logical operations, and to kind of zero out what the pixels would be at that location, followed by an OR to give us the equivalent pixels composited with what our background is to give us effectively a transparent sprite with that particular mask. We don't do that by and large anymore. Even if you were to see something that's kind of a sprite-based engine, it would use transparency values, explicit transparency values. We've talked about this a while. I've used the term. We worry about RGB as our color attributes. We know there's always that 4th color attribute there. That's our color. That's our alpha channel or our transparency channel. That allows us to determine that when we want to specify a triangle, it's not just some combination of red, green, and blue. It's going to have a certain amount of transparency associated with it or opacity associated with it. If it's completely opaque, that would have an alpha value of 1.0 or full alpha. Completely opaque means give me just the RGB, no light is passing through it. If it's completely transparent, then actually the RGB value doesn't really matter as such. All the light is passing through it. It's whatever was behind it is what we actually want to see. And then between the extremes of 0 and 1.0, we have partial transparency or translucent surfaces. We want to pass a little bit of light through this primitive to whatever was behind it. That is what we use the alpha channel for to calculate what that value would correspond to in practice. It's going to be a combination then of the value we currently have in the frame buffer at that location, as well as the fragment we're currently generating at that particular point in time. And it's going to be some just weighted combination of the two, and that's what our alpha channel allows us to determine. This is a red triangle, but it's got an alpha value of 50%. So when I render it, I want it to be red, but I want to combine that red in 50% weight here with whatever happened to be at the frame buffer at that location at that point in time. Alpha is in some sense a complementary approach to working with depth buffers. You can do both. The results aren't always that obvious because we're making kind of 2 different decisions here. Again, you can do both, but oftentimes we do one or the other at one given point in time. With the depth buffer, we have our fragment coming in. We have to determine, do we want this fragment at all or not? We're doing a depth test. We're dropping it if we don't want it. With alpha, we want it. We're just having to determine, well, how much of what was already there do we also want? How do we want to combine, basically still this operation, how much do we want to combine with what was already there previously? So you usually, you can do both, but oftentimes you separate the 2 concerns. For certain things, you want to do blending. For other things, you want to determine depth. You can also think of the alpha composition and the alpha blending as being effectively a floating point version of this blitter hardware that we have here, where instead of just determining what passes a 1 or a 0, we're just determining the magnitude of how much we're blending those 2 values together. It can get a little messy only because in OpenGL and other programming frameworks, It's not a single alpha value we're potentially interested in. We are going to potentially store alpha values corresponding to both the source and both the destination. So it is not so different from the 1-bit case. But then we're keeping track of alpha, not just a single alpha value per fragment, but a single alpha value per color channel associated with the fragment. So it winds up being a lot of things to kind of track. It's still multiplication and addition, so the arithmetic isn't any harder that you have to do in your render output stage. But potentially now you have a source pixel, you have a destination pixel, and it's an RGBA value, or alpha, it's fine, RGBA. You then specify not just a single blending component or a blending factor, you can specify it independently for both how much of the source we want to keep and how much of the destination we want to keep. And you can specify that separately for the RGB and A components of those individual source and destination. So that's a lot of things to specify. I find a lot of those values are kind of hard to reason about, to be honest. Like, what does it mean when I want to take 30% of the green channel but 60% of the blue channel? Likewise, you're then also blending the alpha values themselves. It can be kind of hard to reason about over time what the actual transparency winds up looking like. What tends to happen in many graphics applications is you use this, but it's something like 0 and 1, or it's source alpha and 1 minus source alpha is very common, such that, yes, technically you can specify 8 different blending components. You really oftentimes just specifying 1 is a much more common thing, but you have the flexibility to do so. Once you have those source and destination blending factors, this is another calculation now your render output would then need to do. Every time, if alpha blending is turned on, every time I want to write something, if depth testing is turned on, you first check to see if it passes the depth test or not. If it passes the depth test, you then have to now read from not just, we already read from the depth buffer, we have to read from the frame buffer as well to say what was already there. If nothing else, we should have cleared the frame buffer, so there should be clear values in our frame buffer to start with. So we clear or check our destination pixel, we have our potential source fragment here, and then now we have to have, via some driver or other configuration, a set of these parameters that we then determine for just the red channel, ignore the other channels for now. Given the source red that's coming in from our rasterizer, our destination red that we have to now read to determine what was currently there in the frame buffer, and now given some configured source blending factor and destination blending factor, we then are basically doing a weighted sum of source multiplied by its blending weight plus destination multiplied by its blending weight. We do that for all of RGB as well as for alpha. Then that's the final fragment that we write out to our frame buffer at the end. I think it could be a little hard, although in the basic case we can see, if B, that vector, was set to all 1 and C was set to all 0, then we'd be in that overwrite mode. We'd be in mode 3, effectively equivalent of mode 3, where we just take the source and we overwrite the destination. Likewise, one can imagine a scenario in which B and C always add up to 1.0. So whatever it may be, but we take the value of B and it's a weighted average effectively of how much of our source are we taking in versus how much of our destination we're taking in for each of these channels. But if B is equal to 0.75 and C is equal to 0.6, it gets very hard to reason about what should the actual result be and what are you trying to specify visually. We can kind of work through some of the factors that OpenGL provides for us kind of out of the box. You have to turn on blending and specify, basically that'll be a single bit of configuration in our render output saying, okay, just like we do have to enable depth testing too, but we're going to enable blending, blend everything that comes forward, and then we can specify, kind of separate from all the other programmable stuff that we are doing here, what blending function do we want to use. This can also be done in Fragment Shader itself, but this function is still allowed as kind of a effectively state machine or fixed function piece of hardware that in render output is going to do that extra read, modify, write operation after potentially any depth testing has been done. In the GL blend func way of doing it, there's just a few number of these factors that are supported, where you have to specify this is effectively our vector B, this is effectively our vector C here, and you can specify a few kind of hard-coded examples. Give me source alpha and 1 minus source alpha. That's a pretty good way of doing it. You say, I want to keep 75% of the new pixel and 25% of the old pixel. Or conversely, whatever's currently there, give me that percentage of the alpha there, add on whatever we're adding on here. The source doesn't worry about its own alpha channel. We could also do 0 and 1 combinations. Don't give me any of the source, well, what was the point? Or don't give me any of the destination, overwrite what was previously there. I have a brief demo, which I think will show you why it's a little hard to reason about what the actual fragment color should be. And so testing this, I think, is a little difficult. You should be able to see blending. So I think when we test this in MP4, you'll see that it's not fully red anymore. And I think if you've seen that, you've made pretty good progress. Is the fragment the exact right weird shade of purple that we want it to be? Is the kind of thing you can test. But that is a little painstaking, but you can certainly get to a point where you test it. This is another little OpenGL demo app that should let us specify what we want the blending function to be, but it doesn't tell me what it is. It's just different combinations here. If we assume red is the first thing drawn, then green, then blue, then yellow, this would be, we take the entire source and none of the destination. So this would be the 1 and 0 combination here. I'm gonna struggle to give you the exact reasoning about what the individual pixels should be here, because I can't do the RGB math in my head very well for what's going on here. This is definitely an example of blending in which we are specifying some sort of blend factor here, so that we're getting not just the red and then the blue on top of it, we're getting a combination of the red and the blue to get kind of a purplish kind of result that we have here. But I think for now, and then this one is definitely taking the destination as well. And you can kind of tell the destination is being taken into account, not just the source alpha in this example, because everything's darker. And everything's a little darker because it's taking that background gray, and it's adding in that gray to the new fragments that are being added on top of it, and taking some percentage of that gray value before we even have any red, any blue, any green, or any yellow on top of it there. And that could be a higher percentage, and again, that's back to no blending there. I think it can be pretty hard, just from personal experience, of saying for a particular blend function, for a particular set of alphas, for any 2 pixels in isolation, you may be able to do the math, pencil and paper. Once you have 50 triangles stacked on top of each other, determining what the exact value of that fragment or pixel should be is, I think, a little bit of a tricky thing to do. But at least for MP4, we should be able to set up a couple of different blending scenarios here and show that, in fact, you get your red and blue and it makes kind of a purple color. That basic math should kind of work for you. We don't have to support all of the different possible blending functions. And when we get to that point in MP4, you'll see the instructions are kind of less vague. They basically say, get blending to work. And I don't define it that clearly that you must get this exact 15 configurations to work, and it must be able to pass these particular demos. At that point, certainly as we're getting closer to the end of the semester at that point, look at the driver code, look at the API calls, get a basic team-based understanding of what you'd like to be able to support, get that working, write an application that shows that it's working, and then that's sufficient. There's no provided test that you have to be able to pass to show that it's working at that point. I thought you had a question. Okay. One final thing, something that would be probably more of a final project than we don't do it in the labs themselves. I talked about this a little bit, that all 2D computer graphics have a fundamental aliasing problem. In 224, if you've taken it, you would learn aliasing with a picture like this, it's a valid picture. It's a high frequency signal that we're wanting to sample, but we're not sampling it fast enough or at a high enough frequency. And consequently, we have this high frequency signal, but when it comes time to reconstruct it, we sampled it relatively slowly, and we think the signal is actually this. Right? If this was our input signal, high frequency sine wave, we sample it at half that frequency, or not at the Nyquist sampling frequency, and we reconstruct it, we get something that's at a lower frequency here. The same issue, while very general to all signal reconstruction, is always prevalent in computer graphics. Because ultimately we have some scene that is defined, as we've seen kind of geometrically, right? Defined algebraically what we have in our scene. And of course, reality has a continuous nature to it, a very high frequency nature to it. But ultimately our screen, although it's 2-dimension, not 1-dimension, is a discrete number of samples. And it's whatever our resolution is for that particular screen that we have here. If we have a 1-pixel screen and it's a 1x1, whatever we put on that, no matter how accurately we do the rendering, it's not going to be a very accurate representation of whatever photo or scene we're interested in. Same is still the case with 1920 or any resolution you can come up with. Maybe there's some fundamental limits of what resolutions would allow for true masking of all the aliasing effects here. But otherwise, for conventional real systems, we always have that issue. We are sampling in 2 dimensions. We get something that is kind of masquerading and looks lower frequency than what it actually is. Where we saw this begin with was a couple weeks ago when we were doing just aliasing of our line rasterization. That's the jagged edges of our triangles as well as for our lines. Our basic brush and ham algorithm, which we're still basically doing in our lab implementation, is ultimately determining, are we closer to the upper pixel or the lower pixel, right? Are we above the line more so than we are below the line? And we went through all the details of that, and the algorithm mathematically was clever in that we got to get rid of a lot of multiplications and a lot of divisions, and it was a lot less arithmetic. But the end result is a line that is ultimately going to be very stair-stepped, where the line itself has a particular slope to it. But the rasterized version of that line, you can think of it as having a slope, but it has discrete intervals associated with it. How discrete it is, how alias the line looks, is going to be a function of what the resolution of our rasterization is going to be. The end result doesn't necessarily look very good. For our purposes, it looks more than good enough. You have to really stare and squint to see the resolution of the particular monitor that we had there. If we were using like 640 by 480, maybe you'd see it a lot more clearly on the screen and it would look more annoying to you. So aliasing, at least in this context for 2D images, that's like the jagged edges, the jaggies on the edges of our lines and our shapes. We draw those lines by sampling at those 1-pixel intervals. We either go over and up or we just go over. That is still aliasing. That is effectively still the same thing as here. We have a line that has a particular slope, but the way we're sampling that line is leading to some discretized version of that particular slope, and it's not going to look as smooth as if we had the original line being rasterized. There are all sorts of approaches to kind of perform so-called anti-aliasing. It's not exactly the same as like what people in W would refer to as like signal reconstruction, but there's a lot of similarities there. One approach is so-called unweighted area sampling. The idea is that instead of rasterizing a line, you treat those edges as kind of a single pixel wide rectangle. When we do the rasterization of that rectangle, we then determine how much of each pixel is actually being covered by that rectangle. So it's not a 1 or 0 issue anymore. It's an average of how much of it happens to be covered, and then you would provide some sort of grayscale value or some sort of weighted value, depending on how much of that pixel is actually going to be covered by that rectangle. If we were only doing line rasterization, that's a pretty good solution. You instead treat them as rectangles. You get something that, again, it's still horribly zoomed in on the individual pixels here, but based on our rectangle, you can say, well, what would be a good example? This pixel is covered to a very large amount by the line, by that 1 pixel wide rectangle. It should be very close to 100% filled in, whereas we'll say this pixel here is just maybe 1/8 covered by that particular rectangle. It should be 1/8 the intensity of the rest of those pixels. And the end result is that. I don't know if you can see what I showed there, but we have a fairly filled in pixel here, a much closer to white, but barely maybe 1/8 intensity pixel that we have there. Zoomed in, it still doesn't look very good because it's still, a line that looks extremely zoomed in here, but it kind of zoomed back out. You get kind of that old school kind of anti-alias kind of look to it, where at least it's smoothed the edges to some extent. That is one approach, not exactly in fashion these days. Much more common approach, although the truth is there's like 70 different approaches that all fall under this umbrella and they're all slightly different. but the big picture concept is referred to as super sampling. Super sampling based anti-aliasing. It at first blush doesn't sound that different than rasterizing a pixel-wide rectangle, but the main concept here is that we recognize that we have an output resolution. Ultimately, things are going to go to a frame buffer to be driving a display at the end of the day, and that's the resolution that we're interested in. There's no requirement that we limit our rasterizer's resolution to exactly that same resolution. Maybe our end result is going to be a 640 by 480. There's no requirement that our rasterizer always rasterize at 640 by 480 then. We can configure our rasterizer to rasterize at effectively a sub-pixel resolution here. That also requires more memory, as we'll see in this approach, because as we rasterize to that higher resolution than we're actually displaying at, we need to have memory to store the results of that entire rasterization. So for us, we have 1080p as our output resolution. We actually have enough capacity of memory, not enough bandwidth, but we have enough capacity memory to say, internally in the GPU, as you're doing rasterization, rasterize at 4K resolution. If you look at what we did for your triangle setup and our viewport calculation, we could absolutely do that today and say, rasterize to a 4K buffer, don't rasterize to a 1080p buffer. All of these super sampling approaches do some semblance of that. So that would be effectively the 2x2 subsampling, where we take what is every kind of visual, physical pixel in our display, and we divide it up into kind of logical or just kind of subpixels. So for 2x2, for every pixel that's going to be on our display in that final frame buffer, we allocate effectively 4 times as much memory, or a 2x2 grid of memory associated with that individual pixel. And then we do the rasterization at that resolution. That doesn't solve the problem. It's still fundamentally this. That doesn't actually change, right? But what it is this at a much higher resolution for our super sampling. And then when it comes time to actually set what our final frame buffer is going to be, we take the higher resolution render that we did, and we just do some sort of sliding window averaging of the results that we would have there. So without anti-aliasing, you have something like this. With 2x2 super sampling, it kind of looks like the 1 pixel rectangle example, except the results would be subtly different. And we're rasterizing effectively 4x the amount of fragments that we would otherwise need here. We then would have one final render output pass that would take our very high resolution render that we did here and just average it by that same kind of grid to get what the final result should be. That should look quite a bit more smooth than doing it otherwise, because usually at higher resolution, effectively, you can think of it as, it's not quite the same, but effectively we're doubling our sampling frequency in some sense, and then we're averaging the results to kind of smooth out the end result here. There are many different versions, so if you see MFAA, MSAA, my interpretation of all the different approaches that you will see out there today is they're still super sampling, but they're recognizing that super sampling gets very expensive very quickly. Just doing the math of 2x2 is 4x the amount of work, right? For your rasterizer, 4x the amount of memory bandwidth to get the result into your frame buffer, and so on. So 3x3 is 9x the work, 4x4 is 16x the work, and there's 5x5, there's 6x6 super sampling examples out there as well. And so when you look at something like MSAA, what they do is they effectively do super sampling, but they take a subset of all the super samples they've created, maybe because the results still look quite as good, but also I think to save on bandwidth as well, and not rasterize the entire thing at 36x the original resolution, which would be quite a bit of pixels, right, that you would have to generate at the end of the day. But effectively, what particular sampling pattern they use, and that does seem to change on almost like a year-by-year basis here, effectively it's the same approach, which is rasterize internally at a higher resolution, consume more memory and more memory bandwidth, and then to get less kind of jagged edges, just average the end results that we get back out to get the smoother kind of equivalent here. This demo is not doing super sampling because I couldn't find a tremendous super sampling demo. This is a so-called accumulation buffer, which in some sense has some similarities to super sampling with an accumulation buffer approach, and I took out all the slides on accumulation buffers I had here. The idea is that you continue to rasterize and you're just storing the actual frame buffer at a higher precision than you otherwise would. And the thought is that also leads to smoothing of it. So, we're kind of a victim of the resolution of our projector and my screen here. This would be the so-called, aliased view of that same sphere and that same cone here. We're a victim of our own resolution here, right? It looks okay, but I think if you were to really look closely, and maybe you can look at the video after the fact, you can really see that kind of jagged edge that is happening here. This down here is a texture, so the game is a little bit different with how we're going to do our anti-aliasing with textures here. But still, you can kind of, if you were to stare at it, you can kind of see that stair-stepper kind of approach on the edge of that cone, or what equivalent of the triangle would be on the edges of that cone. If you can't see it, take my word for it. I don't know what else to tell you there. But with the anti-aliasing view, there's a trade-off there. So when you do that anti-aliasing, and let's go back before I have the big reveal here. When you do this anti-aliasing via supersampling or via that accumulation buffer, it should be smoother. So we are smoothing out that function. We are not, though, ultimately reconstructing the original signal back. So it's going to look less jagged because we are fixing this problem of we go up or we go over, pixels on or pixels off. We do fix that problem. But ultimately, depending on the method used, depending on how much supersampling we use, and that's what some of the different patterns that people apply are trying to improve upon that issue, ultimately the end result might look a little smudged. And I think in this example, whether you can see it or not, the jaggedness will be gone. If I go to my anti-aliased view, it is now, I don't know, maybe front row has a slight advantage here. You can kind of sort of see, yeah, it's okay, don't worry about it. You can look at the video afterwards and zoom in, and I'll upload this at high enough resolution today. It is smoothed out. To some extent, though, it's also a little blurry as well, and that's a subjective thing, though. So there's no this is the correct way to do it, this is an incorrect way to do it. You're making a trade-off of kind of how much you're discretely stepping as you go from pixel to pixel to how much you're kind of just averaging everything together and getting ultimately kind of a blurry average of all the fragments that you potentially would have there. Let's leave things here for today with our aliasing and anti-aliasing. On Thursday, we're going to start talking about shader language and shader architecture, and MP3 pre-lab is a good place to get started. It's new, I understand that. It shouldn't be so incredibly foreign that you can't handle it. So work on that as a team tonight. MP3 will start a little slowly, and I think that's okay as you kind of build up a plan. You can't just dive into it and start coding. You shouldn't do that anyway. You definitely can't do that for MP3. So take some time with MP3. You'll have enough time to get it done. We have spring break next week. Unless everyone agrees that we should just come back next Tuesday for class. I'm looking around the room. No one's interested in the idea. Okay, let's leave things here for today. I'll see people on Thursday, and good luck with MP3.